Hi there, welcome to lecture 25 of Machine Learning from Data. And I'm going to tell you about this kernel trick. It's a fancy mechanism that allows us to use the nonlinear feature transform without actually visiting the nonlinear feature transform space. Okay, so that's quite magical. Okay. But before we get going, let's have a quick review of what we have covered so far with respect to support vector machines. And last lecture, I basically offered you evidence that the maximum margin or a large margin is better. And we saw that it improves overfitting and you can get a bound on the out of sample error in terms of the number of support vectors. And what's interesting there is that we control the out of sample error using quantities that do not intrinsically or directly, explicitly depend on the dimension. Okay. We then extended the support vector machine to the non-separable data case. Okay, so it's often the case in practice that your data is not linearly separable. One approach is to tolerate error. And in order to do that, we introduced these, margin penetrations. For each data point, you allow, the data point to penetrate the cushion. So that becomes a soft margin now. That's captured by these xn's. Those xn's then become parameters in the quadratic program, and when you solve this quadratic program with the variables b, w, and c, you end up with the soft margin separator, with some data points perhaps piercing the margin. Okay. Now, this introduces a trade-off between how much the data points pierce the margin, the sum of the x's, and the norm of the weights, the thickness of the margin. A trade-off between in-sample error and regularization, and that trade-off is controlled by a regularization parameter c. Okay, and it's reasonably important to choose this parameter, so you can use cross-validation to do so. The other way to tolerate non-separable data and address, fitting the data, getting E in small, is to use a nonlinear feature transform. Okay. And I demonstrated, last time the third order polynomial transform, and if you did regression for classification, it overfits like crazy. Okay. If you use the optimal hyperplane in the third order feature space, third order polynomial feature space, or the second order polynomial feature space, they give comparable fits. And that's quite miraculous. Even though the third order polynomial space has many more dimensions to play with. And this can be seen by the straightforward regression for classification overfitting like hell. Okay. Even though you have many more dimensions to play with, this constraint of maximizing the margin, this regularization constraint of making you robust to input noise, effectively simplifies the hypothesis. Okay? And how we see that is, even though we have many more dimensions to play with, comparing the third order polynomial transform to the second order polynomial transform, what matters are the small number of support vectors that actually dictate the boundary. Okay? And so even though you have many dimensions, a few support vectors means that those are the parameters that control the boundary. You have a few support vectors to play with. The separation boundary effectively becomes simple. Okay. And this is also, evidenced by the fact that, we derived those theorems that, control the out of sample error, the cross-validation error, in terms of the number of support vectors, which doesn't explicitly depend on the dimensions. As long as the number of support vectors is small, the effective complexity of the hypothesis is small, you're in good shape. Okay. And this raises the possibility that we can perhaps go to larger and larger dimensions, infinite dimensions maybe. Okay. So let's see what that would entail. And let me first show you just a quick review of the mechanics of the nonlinear transform. So you take your original data, okay, you transform it into your nonlinear feature space. Okay. Then you implement the linear model there, but now we're going to implement the optimal, the support vector machine, the one that maximizes the margin, or you can also tolerate error in this space. So you could do the soft margin hyperplane, but whatever your favorite linear model is, you implement that, and then you classify new data by transforming into this space, classifying here, okay, and then reporting the classification. Okay, and so that effectively produces a nonlinear boundary in your original space, even though the boundary is linear in the nonlinear feature space. Now, this entire mechanics relies on taking the data, the original data, and transforming it into the Z space, the feature space, and then performing your linear model there. Okay. And that is a physical constraint that would prevent us from going to huge dimensional spaces or infinite dimensional spaces, just from the computational feasibility of this process. Okay. So today, the main goal is to see how can we implement the nonlinear transform without physically transforming into the Z space. So think about what that is going to buy us. Okay. On the one hand, we see that the optimal hyperplane, controls, the generalization error, controls the overfitting, almost independently of dimensions. We can go to higher and higher dimensions. Okay. And then if we have, on On the other hand, a method for going to higher and higher dimensions without actually physically having to go there, without enduring the computational burden of going there, then if we combine these two, it says that we can efficiently, run nonlinear transforms in huge, perhaps infinite dimensional spaces. So that is going to be the miracle of today. We're going to see that it is indeed possible to perform the learning, to use the linear model plus a nonlinear transform into an infinite dimensional space. Okay? And then the support vector machine, the optimal hyperplane, the maximum margin comes and controls overfitting. And so then that allows us to do learning in infinite dimensional spaces. That's a miracle. Okay? And in order to do that, we will see that all we need is this very simple idea called the kernel trick. We have to massage the learning problem, the optimal hyperplane algorithm a little, but at the end of the day, it's this very simple idea called the kernel trick. Okay, so let's go to the board. To develop this magical ability to, be able to use the nonlinear feature transform without actually jumping into this nonlinear feature space, we're going to have to do some technical derivations and look more closely at the optimal hyperplane algorithm, this quadratic program that gave us the maximum margin hyperplane that separates the data. Okay, and so for the moment, we'll just focus on the separable case, and I'll show you the update when we need to deal with non-separable data. Okay, so first, let me show you that optimization problem, that quadratic program that gives us the optimal maximum margin hyperplane. Okay, so we needed to find the weights W and the bias B. So find the weights W and the bias B that minimize the norm of the weights, 1/2 W transpose W. So minimize the norm of the weights with respect to your parameters, which are W and B, subject to fitting the data. So Yn W transpose Xn plus B is greater or equal to 1. And this constraint must hold for all n equals 1, 2, up to big N. Okay, and just by way of a summary, let me note that this is a quadratic program, and what are the variables? What are the optimization variables? W and B. So you have D plus 1 optimization variables. Okay, and you have n constraints. So you have a constraint for each data point that says that data point must be on the correct side of the hyperplane. And we can use the nonlinear transform and run this quadratic program in the nonlinear feature space. And the problem is that you're going into a D+1 dimensional feature space, and into a D+1. If you're going into a high dimensional feature space, you'll have D+1, whatever that dimension is, optimization variables, and that gets cumbersome. Okay, so this is really what we're going to address today. Okay, the fact that you have D+1 optimization variables. So can we actually get away with infinite dimensional, quadratic programs like this? Okay, so that's the goal. Okay, and in order to get to that goal, we're going to have to transform this optimization problem. We're going to have to massage it into what's called the dual form. So this is, we will refer to this as the primal form of this maximum margin algorithm. Okay, so we have to solve this optimization problem, and we'll just refer to this as the primal version. Okay, and it turns out that this optimization problem is equivalent to another optimization problem. Okay, so is equivalent to another optimization problem. Okay, and this is the dual version of this optimization problem, or the dual form. Okay, now these words are not so important, but the point to sort of appreciate here is we're going to have to massage this, okay, and somehow deal with this high dimensional optimization problem if D is large. Okay, and so what is the dual version? The dual version of this optimization problem, and it looks totally different. Okay, the only thing that you might be familiar with in some sense is the notion of Lagrange multipliers, and you'll see why Lagrange multipliers are necessary, because we have inequality constraints, and whenever you have constraints, then Lagrange multipliers play a role. Okay, so in the dual version, let us introduce for each constraint a Lagrange multiplier. So there's alpha 1, alpha 2, alpha 3, up to alpha n. Okay, which we can summarize in a vector alpha. Okay, so you can think of these as Lagrange multipliers. Now don't worry so much about about the notation. Okay, what I'm saying is that this optimization problem is equivalent to another optimization problem, which is minimize. Now, with respect to these parameters, so minimize with respect to alpha. Okay, 1/2 the sum from n equal, but there are big N parameters, so the sum of from n equals 1 to big N, the sum from m equals 1 to big N, okay, of alpha n, alpha m, yn, ym. So what are yn and ym? They're the same, the target values in the data. xn transpose xm, so put this in parentheses. So what are xn and xm? They're the same, they're your data points. So this is the dot product between xn and xm. Okay, so minimize this quantity minus the sum of the alphas, okay, subject to, okay. So the Lagrange multipliers must be positive, and they in some sense must sum to 1. Okay, well, technically speaking, a signed version of that. So such that the sum over n alpha n yn is equal to 0, and the alpha n are all non-negative. Okay. So this is the dual version of that problem. So when you solve this problem, the output is W star and B star, the optimal hyperplane. When you solve this problem, the output is alpha n star. So this is an optimization problem in these, apparently weird, peculiar parameters that have popped up. Well, they're not really parameters, they're optimization variables. So you solve this problem, you get a bunch of, alphas that, are the solution to this problem, are the optimal. Okay, just like here, if you solve this. And this, it turns out, is a quadratic program. So we can write this. So this guy here can be written, okay, in matrix form as alpha transpose times a matrix G times alpha, okay, with the 1/2. Minus 1 transpose alpha. So it is a quadratic form. Okay, and these constraints are all linear inequality or equality constraints. So this constraint is subject to, so minimize this guy over alpha, subject to y transpose alpha equals 0 and alpha greater equal to 0. Okay. So this is a quadratic program. We can solve it and get alpha n star. Okay. And in what sense is this equivalent to that? Okay, what that means is that if you solve this problem and get the alpha n stars, then I can give you the solution to this problem in a relatively easy way. Okay, and what's that easy way? Well, it turns out that when you solve this problem and get alpha n star, we can figure out what W star is. W star is equal to the sum from n equals 1 to big N, alpha n star yn xn. Okay, very simple. So the W star is a linear combination of your data points, okay? And the coefficients multiplying each data point are the optimal alphas that came out of here, the target value, and the data point vector itself. Okay, what about the optimal B star? The optimal B star is a little more complicated. B star is equal to, okay, now you have to pick a data point, okay? And you have to pick a data point, so you have to pick an alpha whose value is strictly positive. So the alphas can be either 0 or strictly positive. So pick S such that alpha star S is greater than 0. Such an S is called a support vector, and we'll see why shortly. So such an S is called a support vector. Okay? And then B star is very simple. It's just YS, the Y value for that support vector, minus this, the optimal weight vector, the optimal weights W star, transpose the X, the data point XS, so the support vector data point. Okay. And so if you solve this problem, you get the alpha n stars. Okay. We can get the optimal weights W star, and we can get the bias B star, okay, by picking a support vector whose alpha value is positive and just constructing this quantity. That's the bias B star. So it's in that sense that this is equivalent to that, because if I can solve this, I can get a solution to that. So solving this problem essentially could be done by solving this problem. Okay. And why do we do all this? What the heck? Why do we care? Okay. Well, so let's look at this problem. Okay. What are the optimization variables? There's alpha. So how many are there? There are n optimization variables. So n optimization variables. Okay? And how many constraints do we have? Well, we have a very simple constraints. An inequality constraint, y transpose alpha is 0. An equality constraint, y transpose alpha is 0. And then very simple inequality constraints. Basically, a non-negativity constraint. So n plus 1 constraints. But these are simple constraints. Okay, wow. Okay, so we did all this work. We take one quadratic programming problem and transformed it into another quadratic programming problem. Okay, and what you will see is that the number of variables here is n, whereas before it was d. So it doesn't depend on the dimension. Okay, and the number of constraints is n, which is also independent of the dimension, just like it was here, n constraints. So that's relatively similar. So what have we succeeded in doing here? We've sort of exchanged d optimization variables for n optimization variables. But where is this n coming from? The n is your number of data points. It doesn't depend on the dimension of the feature transform. So it's dimension independent. Okay. So where did the dimension disappear? It appears that we have gotten rid of the dimension of the space completely from this problem. Not quite. Okay, so if you look closely, there's something in here that still depends on the dimension. Okay, although the first thing is that, here we have xn transpose xm, the inner product. Well, that's, you need to know xn and xm. So you need to be able to compute this inner product. Okay, so there is a indirect, implicit sort of dimension dependency here. But also the dimension reappears when we come to reconstruct my weights. Okay, to reconstruct my weights, my optimal weights. Okay, I sort of expand it as a linear combination of data points, and those are living in this d-dimensional space. So the dimension does live in here, okay, but we have succeeded in getting rid of the dimension explicitly from the optimization problem. If we could somehow evaluate this dot product without going into the high dimensional space, okay, and then we still need to deal with, well, how about, computing the optimal weights? Well, okay, why do we need the optimal weights? We need the optimal weights in order to perform the classification. So if we can get away with performing the classification without explicitly computing the optimal weights, then we will have succeeded in completely removing the dimension of the space from this problem. And if we can completely remove the dimension of the space from this problem, we can go to infinite dimensions, any dimension we want. Okay. And this problem will be entirely determined by the number of data points, not the dimension. So that's the plan for today. And it all relies on sort of the equivalence of this problem and this problem. In other words, if we solve this problem, we can solve that problem. And so, since that is so stunning and it's going to allow us to move into infinite dimensions, we had better prove it.